let's talk about some of these applications and the amount of energies involved, because you might be wondering, well, how many watts, for example, we all know a watt, right? You have a 60-watt light bulb puts out some light, a 100-watt light bulb's a little bit brighter, but these are just light, just puts out a light, and so 100 watts doesn't seem to be that much, because 100 watts is just a light bulb. However, you don't need many watts to operate a laser. So let's go to the first one, a laser pointer. How many watts do you need for a laser pointer? So a laser pointer, you hold it and a beam comes out, you make a little point on a presentation. Well, a laser pointer is less than one. That symbol MW means milliwatt. That's a thousandth of a watt. So 1 milliwatt is a laser pointer. So a milliwatt can be obtained from a little tiny battery. It's almost a nothing battery, and that's all you need. Now, in your computers, you have a CD-ROM drive, and that operates your computer. Well, how many watts does your computer need to operate a CD drive? Well, it's 5 milliwatts. That's nothing. How about a DVD player? We all know DVD players. You use them for looking at movies. That's only 5 to 10 milliwatts. So it's almost nothing. It's 5 to 10 milliwatts is 100th of a watt. Well, how about a CD burner? You've all done that. You go to your computer and you want to burn a CD. That's only 100 milliwatts, which is basically 1/10 of a watt. A DVD burner is a little bit more, it's 250. Well, that's not much energy at all. You can get all this by batteries. Let's go to 1 watt. 1 watt is simply not a lot. I mean, if you had a 1 watt light bulb, you could even see that it'd be so weak. It'd be a little tiny thing. Well, there's a current technology which is trying to make holographic discs. It's not out in the market yet, but they only use 1 watt for that. So that's all that's going to take when you finally see holographic discs. Okay, now, micromachining. What is micromachining? Micromachining is where they take a laser and they will etch little patterns for circuits in computers, things of that nature. So when you get a computer circuit board, a laser somewhere in some laboratory, probably in China, has used lasers to etch a pattern. That's called micromachining. That's only 1 to 20 watts. So a 20-watt light bulb, in terms of energy, is all you need for that. Now, this is where you get with the more high-powered lasers. As you know, in medicine, they've been you can go in now and they do eye surgery with lasers. If they want to correct your eye, it's called retinal laser surgery. They actually zap a laser beam in your eye, and it goes to your eye and does something. I don't want to get into it here because I'm not a medical person, but it's only 100 watts. So that's like a 100-watt light bulb energy. That's all you need for a surgical laser. Now, when you get to, by the way, those are carbon dioxide lasers. So the gas carbon dioxide goes in that tube I told you about. Now, when you get to industrial cutting, that's where they want to cut metal, like they want to cut steel, or they want to cut glass. You could use lasers for this. They're about 3,000 watts, so they're getting much more powerful. And then you get into hardcore military applications where the United States is very much involved in this, where they want to take a laser beam and they want to shoot down an enemy missile by drilling a hole in it, and the missile might be 100 miles away. How much energy do you need for those lasers? Well, it's 10 million watts. So it's quite a bit more powerful. And finally, I'm going to show pictures of these things, by the way, some of these things. The United States is on the verge of finally harnessing the hydrogen bomb, which is called fusion. As you all know, we've harnessed the atom bomb, which is called fission, and these are your standard nuclear reactors. However, we've never harnessed the hydrogen bomb, which is far more powerful because it's just more difficult to do. It's a very hot reaction. The sun is an example of a gigantic hydrogen bomb that's controlled. It's a fusion reaction. So we've been trying to control fusion ever since hydrogen bombs were first tested in the 1950s, I think. And no one's done it yet. However, the U.S. may be doing it very soon, this summer actually, using a 700 trillion watt laser. out in California, that's 700,000,000,000,000 watts, 700 trillion watts. So that's inconceivable amount of energy, but they have actually built this machine which does it. So let's show some cool pictures. And I have here on the next slide a few cool examples. Now I'm not making a pun here because lasers happen to be hot. So this is a cool example. So I'm only using the cool not in the sense of temperature. It's actually a fun example. I use the word cool because it shows my age. Here's an example, next slide, of an actual laser the United States is testing. This is a airplane, a jet plane, it's an airplane, and at the bottom of it you see a laser coming out, and these are chemical lasers. I told you about that. They're making chemical lasers, and they put out millions of watts, and it shows it zapping something on the ground many miles away. I think the zapping part's actually an animation, but this is what this looks like, and they actually have developed this. I don't know how serious the U.S. is using these things, but it's like a Star Wars kind of weapon, and they do have them. And this is on the web. I'm not using anything here that's not on the web, just so everyone knows this. This is not secret or anything. Now, I'm going to show you a picture which shows how these people think lasers might be used in case there's a missile attack. Here's a picture Air Force people love to show. If you go to Air Force conferences, they love to have pictures like this of a high-powered laser beam on your lower left, this big device with missiles coming in, as you can see, and it's zapping out the missiles that are about to hit that city down there to the right. Now, in reality, I don't think you could ever do this, because I think that all you would have to have is one missile go off, and that's all you would need, and that city would be gone. So there's no room for error. But it makes nice slides, so I think it's a fun-looking slide, although I wouldn't want to be living in that place with those missiles flying around. The next slide is that machine I told you about, the National Ignition Facility, which is making a 700 trillion watt laser. And this is the building it's in. And if you look way up on the upper left, you see little tiny doorways that show you the scale of this. This building is probably a quarter of a mile long, or a half a kilometer long, and it takes hundreds of laser beams on the right and the left that you can see, and at the lower right it focuses them all to one big chamber where they all come out and hit an object about the size of a dime. So it's a little tiny object, and they put isotope, a version of hydrogen in there. It's called tritium and deuterium, and they hit it with 700 trillion watts. It's only on it for a fraction of a second, and they're hoping that they're hoping that the little tiny sphere of deuterium and tritium will actually make a fusion reaction and actually give out more than 700 trillion watts. So they'll get more energy back than what they're putting into it, and that would show that you can actually make a usable fusion reaction. And if they succeed, this will be very, very exciting. And you'll definitely know this by the end of the summer, because if they succeed, it'll be a top news story. Because there's enough energy for fusion reactions for the world forever. We'll never run out of it, because you can make it out of seawater. You can make deuterium and tritium out of seawater. Okay, this is a picture of that machine, and there's many more pictures you can have. If you Google on National Ignition Facility, you'll see some amazing pictures. Now, you can use lasers in outer space. This is a picture of basically, they want to use lasers to make what's called a gravity wave detector, and I'm not going to talk about this at all here in too much detail, but Einstein, in his work in general relativity, not special relativity, but he had a more fancy version of relativity called general relativity, which says that if you have a highly massive object like a star, then under certain circumstances it can give out waves of gravity. Einstein viewed gravity as a distortion of space and time, and that can be interpreted as a wave in the galaxy that we live in, for example. And you want to be able to see if you can detect those waves. So on the lower right, you see the Earth and the Moon. and there's the sun, and way off in the distance, that represents the center of our galaxy. And on the lower left is basically you see 3 laser beams from these are satellites in space called the LISA satellites, LISA at the top, laser interferometer space antenna, and they make 3 laser beams, and they're separated by several thousand kilometers. And the idea is, if you have 3 laser beams beaming back and forth like that, and a gravity wave goes by, you can detect it. So far, nobody has ever detected a gravity wave. So this is a way to do it. Now you can make gravity wave detectors on the ground, but they're not anywhere as sensitive as this will be, and NASA wants to do this. The European Space Agency wants to do this. So far, no one has ever made a gravity wave detector in space, but that's coming up in the future. You can also use lasers for laser propulsion. If you take a spaceship like this and you hit it with a laser beam, you can have the bottom of the spaceship actually be burned off, but in the process of being burned off, it makes propulsion and it actually gets pushed forward. And this shows a laser pushing a spaceship. Here's a cool picture of one. It looks like a spaceship on the next slide called laser propulsion. The next slide here, by the way, I just want to make sure I got the slides in the order. I'm going now to the previous slide called laser propulsion, which is red showing the spaceship. And the slide before that, I want to make sure that you guys saw that gravity wave detector, which I'm now on. Now I'm going to go forward. So now I'm on the slide called laser propulsion with the red beam hitting the spaceship. And I'm going to the next slide, again called laser propulsion. And it shows a more futuristic looking saucer-shaped craft with a laser beam from the ground hitting it. And then there's a little hole on the top of the craft, and some of the laser goes through, and it illuminates a little tiny object in the front of it, which is being burned off as well, and this forces the whole object forward. So that's pretty cool. This is stuff NASA's working on now, called laser propulsion. And here, your laser is not on your spaceship. It's on the ground or in space, and it pushes your spaceship off. And the idea is, using laser propulsion, you can get spaceships to go much, much, much faster than today. Finally, I want to end this presentation with what you can do if you like, if you're in the arts. Here's an interesting, it's called laser photography in art. So what people do is they make laser beams in the laboratory and they photograph it, and you make these cool looking pictures. I happen to like this picture a lot on this slide I'm looking at now, laser photography in art, and it shows a sphere, as you can see, with, I believe this is all laser light. Somehow they made laser light go through tubing. It's called optical fiber tubes, and they have lasers going through it. And what distinguishes laser light is that it's very, very bright and very intense. So this is an example of what you can do with it. And if you happen to be an art kind of person, I think it's a fun thing to do, is to make laser art.